Okay, 3 lines of code. I've got myself the derivative matrix that I need. Yeah. Yeah, we can put it in either here, or we need to make sure to include it in. But notice that my dt and my dx I want to wrap up in my lambda. Right? So my CFL condition, remember in this time-stepping scheme, you've taken out the 1 over 2 dx on the bottom, and you've thrown it into your CFL lambda number. So what we're going to do is what we have left over is point in front minus point behind. So if you go right behind here, which is really easy to see, right here, if you can see this. Yeah, no, you can't see that? Okay, all right. So right behind there, right, we have this scheme which has said point in the future is what it is now, plus lambda over 2. So what I've done is I've wrapped up my dt and dx together there. That's the CFL number. CFL divided by 2. And then point in front, point behind. So point in front and point behind are carried by that matrix A. So what we'll do is just leave them in there. All right, so how do we set this up? Now we're going to do an iteration scheme for j equals n. From 1 to something, we should start somewhere. 1's a perfectly good thing to start with. And we should step forward into the future. How far are we going to go? Well, we're going to go actually to the length of that vector t. If you remember, here's t. T goes from 0, steps of dt, all the way up to time 4. So this here tells me goes from 0, 0.2, 0.4, 0.6. So I want to run a loop that goes all the way to time 4, and this is how I do it right there. That's my loop. It's going to go through all of time. Okay? And what I want to do with this, well, what does Leapfrog tell me to do? Leapfrog tells you to say, look, you have your point in the future is what it is now, plus lambda over 2, or CFL over 2, times that matrix. So what I'm going to do is just basically say the following. Let's call U1 my future point. It's what it is now, plus CFL over 2 times A times U0. That, I claim, is the application of what the Euler scheme tells you to do. My point in the future, U1, is what it is now, plus the lambda over 2, plus A times U0. A, remember, has a coefficient of 1 for the point in front, minus 1 for the point in back. That's it. That is your Euler scheme. Everybody go with that? Now, once you step forward once, you have a new U1. Now, U1 has to become U0 if you're going to go through this again, right? So you have to, first of all, we have to figure out how to save the data. Second of all, after we've taken a step forward into the future, I should go ahead and say, okay, now I'm in a loop. I'm going to make U0 is equal to U1. All right? So I have to, once I step into the future, this future point now becomes my current time. So my current time is U0, so I'll recall it U0. And then I step forward into the future, and that future point now becomes current time again. And so you just go forward like this. But it's important that you save your data somewhere. So let's go ahead and start saving data. So what I'm going to do is start here. And what I want to do with this is basically say, okay, this is my initial condition, right? So let's get rid of this for a minute. My solution will be, and this will be the first row of this thing, will be U0. So my first column. So I'm going to save all this as columns. By the way, let's break this here. Let me make sure. Okay. So for instance, U0, size of U0 is equal to what? Okay, what's going on with that? Oh, have I not? So U0's there, so I didn't do a size. Okay, there we go. One row, 200 columns. So in other words, so right now, the way it's written is one big row. Okay? All right. So I think what I want to do is save it as I want to save these as columns. You can decide how you want to do it. So if I want to save it as columns, I can just do that. transpose it. Okay, so what I'm going to do is take this thing here. Normally it tries to make row vectors. Instead, I'm going to make it make a column so that the dot transpose flips it to be a column. And I'm going to line up the first column of this matrix you saw will be times 0. The second column will be time delta t into the future. Third column will be time 3 into the future, and so forth. Okay? And that's how I'm going to line up my data. You can do it any way you want. I'm up here. I'm running the code. I get to pick. So I'll just do it like this. Whatever you want to do organizationally, it's up to you. Okay. So now that I have that, what I can do is come back down to my piece of code here and say, okay, so I've rewritten the future. I mean, literally, I have with generating u0 rewritten the future. And there it is. U0 is the future. So I'm going to say, hey, you know what? You saw. And I'm looking at the jth column now, but not j plus 1, because I already have j equals 1. You cannot index off 0, right? So you have to start with 1. Times 0 is column 1, not column 0. There is no such thing as a column 0, right? So j plus 1 is equal to u0. And I just stack all my data. Everybody go with that? So I have everything there. So I've just captured my data. I've put it all in. And so now we are ready to run this thing forward into the future. But let's plot it. And one of the better ways to plot things is there's the waterfall command. So after I've got all this you saw written out, I'm going to do the following. Waterfall, x versus t versus, turns out I have to transpose this thing. And I'm going to make it black and white. Why do I like black and white? I like black and white because when you go to make a paper for a journal, do you know how much it costs to print color? Well, it turns out a lot. So if you have a rich advisor, you don't care. But if you don't have a lot of money to throw out at journals for $1,000 a page of color, you just say, how about I make that in black and white? Okay. Not to be cheap or anything. I'm just saying. Okay. Let's run this thing. See if it complains. Oh, you might be good to take that break statement out. Yeah. Okay. Take the break statement out and go. Yeah, I knew it was going to complain. It never works the first time. Okay. Do I have these backwards? Let me try one thing here. No. So I should have lined these up. Oh. Let's do one thing. Size, x. Size, t. Size, yeah, so that's the problem. Size, you saw. So they're not all the same size. Okay? So that's typically where the problem lies. So let's see here. I'm going to go 1 to length of t. And actually, I want to go length of t minus 1. The reason I want to go t minus 1, remember, I already got the initial slice. If I go 1 to the length of t, it already had 0 in there. I already had 0, so I don't want to, I'm recounting it. So right, I didn't go to time 4. I went to time 4 plus delta t beyond that. Okay? Now let's try it. Oh, I better put this back in here. Okay. I didn't hear a beep. And there you go. There is my one-way wave. Watch this. Ready? What I suggest you do is hang on to the desk as I move this. So I don't want to make you dizzy. Whoa. Check that out. Kind of looks cool, huh? Here's a wave moving to the left. And this is total garbage. It looks cool. Looks like some other waves are being generated. And you think, whoa, that's pretty cool phenomena. All numerically generated crap. Okay? You have violated CFL. And by the way, if you keep this going, notice what's happening with the amplitude. It starts at 1. Within 4 units, it's starting to get up to 4. If I just keep running this thing just goes to infinity. Completely bogus results. Now, we know this because we did the calculation about CFL, and no matter what I pick delta t to be, this will happen. Okay? So anyway, you don't want to be deceived by such behavior and say, look at this cool, interesting phenomenon. When you throw a rock in the lake or when you get a thing, you generate, things blow up. Now, if that was true, nobody would throw rocks in the lakes because you'd been standing on the shore and a giant wave would have come and knocked you down. Okay? All right, so we have one method here, and we know it doesn't work. So we did the Euler. We see what goes on. Let's go ahead and switch over then to Leapfrog.
So if your CFL is 0.2, then it's still have the same.
Yeah.
It'll be the same crap.
Well, in fact, if you so right now CFL is 0.2. No, so what is it? 2. So let's just okay. So let's cut it down. Let's make it 4 times smaller. So it's going to be a CFL of a half. And what you'll see, the growth is much slower. Hold on. Come on. It will. If you keep running this, like you say, hey, I want to run it out to 100 units, you'll just see this thing blow up. That's the thing it does. Hold on. Okay. So here, you can see it again. It's starting to grow, and it grows exponentially, right? So since it starts getting bigger, it starts getting bigger and bigger. It takes longer. You take your delta t down, but the height here, instead of being almost at 4, it's only at 1.2 or 3. And you can't quite see it yet, but right over here on that little edge there, you're going to start seeing the same kind of oscillations starting to take off.